1-6 deals with velocity vectors. So we're going to first a quick demo, just so you have an idea of how the concept works. This is a plane, and the plane is traveling along this route. Here's a wind, and the wind acts on the plane. So this was the original heading, which is the direction in which the pilot is steering the plane, also known as the air velocity of the plane. However, that's not what actually happens. What really happens is that the plane flies in this direction because of the influence of the wind. And so this is what we call the ground velocity or the bearing. So it would look something like this. That's the heading or the air velocity. This is the wind acting upon it, causing it to instead fly this way, like that. Okay, let me show you another example. So let's say this airplane is flying this way. So it's moving like this, and you have a wind rather, that's acting upon it like this, so that its path instead goes like this. So here's the wind acting upon it, and you'll notice that the head of this vector joins to the tail of the wind, which then the head of the wind joins to this one right over here, to the head of the resultant. So this is your resultant right over here. And oftentimes that's what we're looking for, what really happens to the plane, also known as your ground velocity, and that's the bearing that it ends up having. Now we could have the plane going like this, and let's say there was a wind acting this way this time. So if your wind is pushing it this way, then your plane, instead of flying, like this, will have the wind acting upon it and will instead be going this way after the influence of the wind. And here's the triangle that results from that one. Okay, here's the triangle that results right here. So you have the heading of the plane, you have the wind acting upon it, and this is the resultant. All right, let's take a look at this. So there are a couple of definitions that we have to write down first. And the first one is heading or air velocity. So when we talk about air velocity or heading, these refer to the direction in which the vessel is steered. Now the vessel could be a helicopter, it could be an airplane, a train, whatever. And this is different from your ground velocity, or the bearing, which refer to what you actually see. This is the resultant. Okay. The velocity of the plane. So that's another term. Velocity of the plane refers to its airspeed. Okay. Whereas the velocity of the wind refer to its velocity relative to a fixed point on the ground. Okay. So let's take a look at the first question. You have an airplane that's flying due north, north at 160 kilometers per hour, so it's going northward. There's a wind from the east, so the wind is going this way. Okay, at 75 kilometers per hour. Determine the ground speed and direction of the plane. So as you can see, the plane is not going to stay in this direction, it's going to be going this way. So let's sketch that. You don't have to draw these vectors to scale, however they should be proportional. So the first vector is the plane, which is 160 kilometers per hour, and that's going northward. So here it is. And you have the wind that is blowing from the east, 75, so about half the magnitude, and it's coming this way, right? It's coming this way. So because it's coming this way, we are going to take this vector and we're going to move it over here, and that way we could see it, the influence of that wind, and we get a head to tail situation. So this one was 160 kilometers per hour. The green one was 75 kilometers per hour. I'm gonna write it over here. And our resultant goes from here to here. Remember, that's what's actually happening to the plane. And we're going to label this R for resultant. Okay, so these vectors meet at a 90-degree angle, and if we're first looking for the magnitude of the resultant, then we could simply use the Pythagorean theorem, so that the magnitude of R squared is equal to 160 squared plus 75 squared. 160 squared gives us 25,600, and 75 squared gives us 5,625. So that the magnitude of R, if you take the sum of that and then the root of that, comes out to be 176.7 kilometers per hour. However, a vector has not only magnitude, it has direction as well. So we're going to have to figure out this angle in here, so then we could say that it's so many degrees west of north. Okay. Now to find that angle, I have this side, which is the opposite side. I have the adjacent side. It's a right angle triangle, so it's simply trig ratio. Tangent of theta, opposite over adjacent, is equal to 75 over 160. And angle theta comes out to be 25.1 degree. So therefore, the plane has a ground speed. The plane has a ground speed of 176.7 kilometers per hour. And sometimes you'll see directions written in square brackets, or you could write it with a comma afterwards. And this direction is 25 degrees west of north. So remember, your first letter must be the north or the south, followed by 25 degrees west. Okay, let's take a look at the second question. For example 2, you have a plane that's heading northeast at 500 kilometers per hour, and it encounters a wind of 120 kilometers per hour from 25 degrees east of north. Determine the resultant ground velocity of the airplane. Okay. Let's draw a vector diagram. See what we're working with. And this one is at 500, the other is 120, so approximately 4 times the magnitude of the other one. And it is heading northeast, so it's heading at a 45-degree angle. So approximately something like that. Okay, and that is 500 kilometers per hour. Okay, so we have a wind that is coming from, and that's important, it's from 25 degrees east of north. So an easy way of drawing this is to create another set of axes at the head of your plane vector from here. So this vector, which is about a quarter the size of the other one, is coming from 25 degrees east of north. So this is north, and if I go 25 degrees east, approximately something like that, so I have a vector that's coming this way. It's about a quarter the size of the other one. And I know that this angle in here is 25 degrees, since it was coming from 25 degrees east of north. So 25 degrees east of north would be like this normally, but because it's coming from, you have to kind of spin your vector around and have it coming in this direction. Okay. This vector over here doesn't really help us much. We're going to have to take it and move it down here, so we're joining it head to tail. So I'm going to preserve its direction and just redraw it over here. And that enables us to draw the resultant, which is what's actually happening to the airplane. And it's a vector that looks like this. This is your resultant. So the magnitude of the wind was 120 kilometers per hour. And that's this one over here as well, 120 kilometers per hour. So when I take a look at this, I'm looking for the magnitude of r. We no longer have a right angle triangle, so we cannot use simple trig ratios. We need to use either the cosine law or the sine law. And I don't see any pairs of angles right away, so we're going to have to use the cosine law. We have two sides, so a squared is equal to b squared plus c squared minus 2bc cosine of angle A. We need this angle over here. So if we can find this angle, then we can use the cosine law. Well, we know that this angle being 25 degrees, this is the opposite angle here, so this angle is also 25 degrees. Okay, opposite angles are equal. And we also know that the plane was flying at 500 kilometers per hour in a northeast direction. So if it's northeast, then this angle here must be 45 degrees. And this angle here must also be 45 degrees. Well, if you recall your Z pattern, here's your Z pattern right over here, and this angle here must be equal to 45 degrees as well, right in here. So once you have that, then it becomes easy to find out the missing angle. We know that this is 90 degrees, so 90 degrees, take away 45 degrees, take away 25 degrees, is equal to 20 degrees. So this little angle in here is 20 degrees. So then the magnitude of the resultant r squared must be equal to 500 squared plus 120 squared minus 2 times 500 times 120 multiplied by the cosine of this angle here, which is 20 degrees. When you're working this out, remember that you must do the cosine of 20 degrees first. So I could punch that into the calculator, and I'm going to get, for all of this, I'm going to get minus 112,763.11. 500 squared is going to be 250,000, and 120 squared is going to be 14,400. So when I combine all this together, I'm going to get 151,636.89. So the magnitude of r comes out to be equal to 389.41. However, a vector has direction as well as magnitude, so now we need to find the direction at which the plane is flying at. And in order to do that, if I could find this angle here, angle theta, then I could add that to the 45 degrees to come up with the direction. So in order to do that, I'm going to use the sine law. I have an angle unknown, a side that's known. I have an angle known, and I have a side that's now known. So I'm going to use the sine law. To find angle theta, and that is going to be a over sine A equals b over sine B. So 120 over the sine of theta is equal to 389.41 over the sine of 20 degrees. Cross multiply and you get sine theta is equal to 120 sine of 20 degrees over 389.41, and angle theta comes out to be 6.1 degrees. Now, with that being 6.1 degrees, all we need to do next is to add 6.1 degrees to 45 degrees. So 45 degrees plus 6.1 degrees equals 51 degrees. And therefore, the resultant ground velocity of the airplane is 389.41 kilometers per hour in the direction of 51 degrees east of north and 51 degrees east. Now I would like you to try the next example, example 3, and once you have that completed, or if you're stuck, then you could go on to the next video for this lesson.